welcome to the Learning Series webinar. Today's topic is going to be mechatronics and machine safety. My name is Philip Lucia. I am the mechatronics specialist for the Reynolds company. I'm based here in Farmers Branch in North Dallas, but I cover all of the Reynolds served areas. And I'm going to be presenting on mechatronics basics and the Rockwell portfolio. Then I'm going to be joined by a couple guests. Rob George from Techmation LLC will be presenting on understanding linear motion technology, and Eric Bombier from Rockwell will have a machinery safety update for us. But without further ado, here are some mechatronics basics and the portfolio. So first, what is mechatronics? It's a $10 word, and it means a couple things. One meaning is it's a cross-disciplinary engineering area of practice that originally involved applying new electronic solutions like the brushless commutation drive to perform mechanical tasks better and more reliably. Over time, mechatronics has grown, and it incorporates computer engineering, computer science, robotics, telecommunications, control, and automation. And it's also used to mean motion control and servo components and applications. So for Rockwell Mechatronics, the kinetics products are the core of the segment, whether it's a time-tested solution like a rotary or a linear servo motor or servo drive, or newer tech like independent cart or Rockwell Unified Robotic Control. I'm going to give a little more information on those topics later on. I just want to mention those now. Mechatronics also encompasses some Rockwell software solutions with applications in motion, particularly FactoryTalk Motion Analyzer, Rockwell's full-featured design software for motion system sizing and selection, Emulate 3D software for mechanical and controls simulation, code development, commissioning, and testing of code in a flexible, fully virtual environment. And then there's also Application Code Manager and the Machine Builder libraries for it. Powerful software for developing reconfigurable, reusable, and redeployable code for projects. This is particularly useful with the type of code that we have in mechatronics, where we often need to duplicate, tweak, and redeploy code to control many axes or movers or joints, whatever we're moving. And finally, Rockwell makes many components at the core of the motion system, but most systems have specialized components that are not made by Rockwell, which is where our technology partners, such as Linmot and Macron Dynamics, come in to help. What components create a motion system? I'm going to break this down and try to make it very simple. The motion control axes are going to consist of 4 basic parts. Some of these are present and separate from one another. Some systems have these different axes or these different components combined. But we'll talk through them. A controller is needed for a motion control axis. Sometimes you'll find this being combined with the drive, but in many cases, particularly with Rockwell, it is not. It's a separate component, and it uses the communication layer to pass all of its data, including commands, status, and safety data. Your communication bus is needed for transporting data back and forth. In the past, that's been Circos. There are other competing types of communication buses, but the current greatest state-of-the-art communication for Rockwell is Ethernet IP, unmodified Ethernet IP, which I'll be talking about in a bit. You need a drive, of course. That's a servo drive or a standard duty frequency drive if it's capable of closed loop control, can serve as a motion control axis. And drives have a few different bus technologies. They can have a single bus or shared common bus between multiple axes. You can have active or passive power supplies, depending on if you're using regeneration or not. And then at the core of the motion system is the actuator. That's going to be a motor, which can take many forms: rotary servos, linear servos, induction motors, etc. But there has to be some sort of actuator where the motion takes place. And then that actuator needs to have feedback in order for it to be a closed loop servo. That feedback can have a number of different styles. You can have high resolution feedback, single or multi-turn, absolute. You can have digital feedback. Safety capable feedback has built-in redundancy for safety, and data-rich devices are also available for feedback. Now, while each of these components should be selected carefully, you always start with your actuator first. If the actuator can't deliver the performance that the application needs, then the drive and controller will not be able to make up the difference. The mechanical requirements drive all the other system design considerations in mechatronics. That's an important point to be aware of. Now I'm going to talk a little bit about the kinetics family and the Rockwell motion portfolio. You may be familiar with this already, but in general, the motion product is divided into 2 main areas. There's a general motion control business, better known as kinetics, which incorporates the kinetics drives and accessories, and the kinetics motors and cables. The second segment is going to be the Independent Cart Technology segment, or ICT. This product portfolio includes products like the MagnaMotion Lite, Quick Stick, and iTrack. And I'm going to discuss and show videos of these systems operating a bit later. For now, it's just enough to hear the name. And I'm going to discuss the Kinetics drives now in a little more detail. So there are 4 active products in the Kinetics drive family. These are all Ethernet IP connected drives. The Circos network drives are a thing of the past. These should be targeted as a priority for migration efforts. I'm going to start with the Kinetics 5300. This is the entry-level single-axis SIP motion drive, meaning integrated motion with a Rockwell motion controller. The 5500 adds multi-axis AC/DC bus sharing and single cable motor support. So you can use these with the newer single cable servo motors. And the 5700 is the flagship Kinetics drive for large machines. It has many configurable options, and it has the most advanced auto tune and safety features. The Kinetics 5100 now is a standalone Ethernet IP single axis indexing drive. This means it does not require or use the integrated motion features of the Rockwell ControlLogix and Compact Logix PLCs. In fact, the 5100 can be used with a micro series controller or without any controller at all. But the 5100 does provide lower performance, and it lacks certain features like multi-axis coordinated motion, most importantly. Now here's an overview and a way to think about the options in your current Kinetics rotary motors. If you look at the top row, there are still classic twin cable servos like the MPL or the MPS stainless steel with a power cable and a separate feedback cable. But now consider newer options like the single cable VPL or VPF hygienic design, VPF food grade design, which is compatible with the Kinetics 5500 and 5700. And then the hygienic design VPH, which is designed with features for prevention of microbial growth in sanitary applications. So the MPS is a stainless steel motor. The VPH is a hygienic design motor. They're similar, but there's some differences. There are also newer high-powered and feature-packed MMA mains motors that replace the older HPK mains motors. And in addition to rotary motors, Rockwell also offers rugged and powerful linear motors and actuators in various styles. These do tend to be larger and more powerful than the products available from our technology partners, which Rob is going to discuss in a few minutes. There are products available as component kits for OEM integration into the machine, primarily with the linear motors, although you can also obtain these as complete linear stages and thrusters ready for retrofit on old machines to replace existing hardware. And there are rod-style linear actuators ready to upgrade costly and leaky pneumatic and hydraulic systems. These linear motion products are fully integrated with the Kinetics drives for a complete system solution, and many third-party linear products are also integrated similarly, if not exactly the same. Here's a brand new product in the Kinetics family, Armor Kinetics distributed servo drives. This was just introduced, and this is an on-machine servo drive platform based on Kinetics 5700 and offering the same great advanced features in a new form factor with some serious advantages. I'm not going to have time today to get into all the details of this product, so feel free to pause if you're watching this recorded and reach out to myself or your account manager if you have any questions or see anything that catches your interest. Like I said, Armor Kinetics is an extension of the 5700 platform with all the unbeatable features of that flagship drive, while also equipped with some new advanced sensors for enabling predictive analytics, all in a compact on-machine footprint. The advanced integrated safety features pair perfectly with Rockwell's other machine safety solutions, which Eric will be discussing shortly. There are 2 versions of Armor Kinetics to be aware of. There's a DSD distributed servo drive, which is an on-machine servo drive. It has a short cable run to the motor, and it can also be used as a feedback-only half-axis, so you get 1.5 axes with the DSD. It supports the largest variety of motors and actuators. The DSM is an on-machine servo drive with an integrated VPL motor, so there's no cables to run between drive and motor on this, just the cable to the drive. Both of these versions use a daisy-chainable special single cable that transmits power, feedback, and data to drastically reduce enclosure sizes by moving the access modules out to the machine and slashing cable runs and install time, since you no longer have 2 cables going back to the panel for every single motor. There's a lot of information on this slide. I'm not going to read it all. The benefits of on-machine drives are many, though, from increased uptime because of improved mean time to restoration and quicker diagnostics and replacement, to reduced total system installed cost and increased productivity and sustainability as indicated. The bottom line, if you have an application or you're interested in exploring on-machine servo control, please reach out to your Reynolds account manager today. Okay, now looking beyond drives and actuators, Rockwell Premier Integration is the system architecture that brings together traditional rotary and linear servo systems with other components as diverse as robot arms and independent cart conveyors. Develop machines using the same architecture for mechatronics as your safety and sensors, visualization, and other software and hardware product extensions. This brings me to the independent cart technology products. Our independent cart technology portfolio represents the largest in the industry and allows us to cover a huge range of applications, whether it's between machines on the plant floor, as in the case of MagnaMover Lite and QuickStick, or for conveyance within a machine, in the case of iTrack, and from 1 kilogram payload up to thousands of kilograms. I'm going to show some brief videos now to demonstrate the different options in the ICT family and to give you a sense of how these products work. Here's a video highlighting life science and medical device applications for MagnaMover Lite. The MagnaMover Lite intelligent conveyor system is a self-contained transport system of passive magnetic pucks and intelligent tracks, designed to perform traditional belt and chain conveyors and routing small loads quickly and efficiently. The designer lays out grouping and sortation and defined buffer zones and enables production load balancing and product sorting. The system can be laid out in virtually limitless configurations for scalability and modularity, and are optionally available with IP65 rating for saving valuable space and cost in clean room environments. Up to 1/3 of the floor space can be saved. End-to-end tracking and tracing is a snap with MagnaMover Lite, and you can provide process documentation to your customer for each and every unit. Next is a video showing a switch track application in the automotive industry using the QuickStick system. This can help remove non-productive buffers by efficiently routing product with high precision, repeatability, and flexibility in layouts. You can dynamically group similar products at stations to level load production and enjoy the freedom of infinite layout flexibility and increased speed and acceleration through defined safe zones. QuickStick is similar in concept to MagnaMover, but it is capable of larger payloads and offers more customization in terms of movers and their support structures for customers to choose components that work with their system. And last, there's iTrack. This video is from a customer, Stax Technologies, that shows iTrack in a typical bagging application, in this case for tissue rolls. The iTrack system offers fast, precise in-machine conveyance with supreme flexibility. Because of iTrack, this machine is shown here bagging 4 tissue rolls together at high speed, and then with single button or no button changeover to accommodate a different quantity, in this case an 8-pack of tissues, and it can change form factors dynamically and programmatically, enabling numerous SKUs to be packaged by a single machine. That's the power of replacing traditional fixed conveyors with iTrack and independent cart technology. Now, shifting topics from ICT to robots, engineers have options to integrate robots into Rockwell systems today using 2 integration methods, one old and one new that I want to talk about. The old method is with an Ethernet IP connected third-party robot controller, usually 1 per robot. There may be a separate programming software that needs to be learned. The Logix controller executes machine code using add-on profiles for tag mapping and add-on instructions with the robot, which the robot controller translates into movements. However, you are at the mercy of the controller and your performance will never exceed its capabilities. Now I want to talk about unified robotic control, which is the new robot control method from Rockwell. This is for direct integration of robot arm joints to the Logix controller via kinetics drives. This enables the highest performance and dynamic pick and place applications. With Rockwell's kinematics and motion instructions, you can develop code in a familiar environment using Emulate 3D and Logix Designer, and then you can deploy to the PLC and drive and enjoy. Targeted support is available for select partner products, and I've got some slides about those partner products. The first partner is Comau, and they have a series of articulated robots with different payloads. There's also some SCARA options. The other partner is Autonox with Delta robots for high-speed pick and place with a few different options for various degrees of freedom that are available. For more information on URC, contact your Reynolds account manager or myself. And finally, I'm going to highlight some of the partner technologies and tools that Rockwell and Reynolds can provide for you. First, here's a quick rundown of the sizing process, just to give you an idea of what I'm looking for when you contact me with an application. Starting from left to right, we start with the mechanics of the application. What are the shapes, sizes, and mass of the components that the motion system is going to be moving? How much load inertia is the drive going to have to overcome? Then we develop our worst case motion profile. How fast and with how much torque or rotational strength must the components be moved to perform the required machine operation? Our goal is to calculate the intermittent or peak and also continuous equivalent, or root mean squared, output speed, torque, and ultimately power. This defines our basic set of requirements and lets us choose components to match them. Then we determine our full system requirements and we iterate to reach the optimal solution. We begin looking at individual part numbers, which is generally starting with the motor, although having a gear ratio in mind at this stage can be helpful, knowing that it can change later. We select a motor and gear with enough speed to cover our fastest moves and enough power and torque to complete them in a controlled fashion without overheating. And then we work backwards to determine what other components are needed to fully power and control the motor. Then we iterate the entire design by looking at another possible solution combination or more, often with a different motor or gear ratio, and we see what impact that has on the system's ability to execute the requirements. Once we have a sizing that we're happy with and determine is optimal, then we select all the other components to support and backstop the motor and drive. We activate the supply chain and we get the parts that we need. One of the tools that I use, I'm going to talk real briefly and have mentioned it before, is Motion Analyzer. This saves time over historically having to do this process with pen and paper or mathematical calculations on a calculator. Motion Analyzer is a full-featured motion sizing program. It is available for free from Rockwell's PC-DC, and it's a cloud-based application as well. So there's now an online version and an offline version with very similar features. The only difference that I'm aware of right now is some of the sharing features aren't present in the offline version. The cloud-based application conveniently and securely stores projects and components for users in the library. You can recall projects and modify them, reuse them, share them with other users. But at the core of Motion Analyzer is the performance analysis. Users can take advantage of access level or bus level analysis, and they can compare their application performance to the rated performance of the component or system that they have defined to make sure everything is performing as intended. And then lastly, Motion Analyzer also has the ability to exchange data with other Rockwell automation software like Studio 5000 and ProposalWorks. Motion Analyzer can exchange motion data with Logix Designer in Studio 5000 and generate a bill of materials with ProposalWorks. It's a powerful tool, and if you're interested in motion sizing, I do recommend you playing with it. Contact me for more help. And last, here's our line card of Mechatronic technology partners. Going through all these and their products is going to have to wait for another day, but these are the names that we at the Reynolds Company trust for quality mechatronic components to create a complete solution out of a Rockwell integrated motion system. That's going to do it for me today. Next up is going to be Rob George with Manufacturers Rep Techmation LLC to present on understanding linear technologies, featuring many of these same names. Thanks, Rob. Take it away.
All right. Well, thanks, attendees. I appreciate the time and the opportunity to talk to the Reynolds team and their customers. So I'm Rob George of Techmation. We're a rep company that works within the Reynolds branches. This presentation was developed by Michael Genta at Macron Dynamics, who does quite a bit of business with Reynolds and Mac nationally. So this is a base presentation to kind of get us what is linear technology and what are the different types. So the scope of this project is to really help you understand, select and apply the correct technology for the application. And we're going to go through 6 different types of commercially available actuators and just outlining the pros and cons of each. This is going to be kind of vendor agnostic, so it's just going to be more of a baseline entry level discussion. So what is linear motion? It's basically motion along a straight line, and that's kind of the bottom line. And it can be described mathematically using only one spatial dimension. It's a lot of $5 words, but really, what is it? It starts with the base technology, or kind of the most entry level of pneumatic cylinders, hydraulic cylinders, screw-driven actuators, belt drives, linear motors, and rack and pinion. So what is the difference between a rod style and a carriage style? Basically, on a rod style on the left, let me get my laser pointer. The carriage moves along a bearing structure in one axis. A rod style is you have a fixed point of contact, either a trunnion mount or a flange mount, and the shaft goes in and out as such. So starting with the most basic, pneumatic cylinders. So kind of to describe how a pneumatic cylinder works, it's pretty basic. You have a manifold with air, pneumatic pressurized air that either goes to the left or the right side of the actuator. The air comes in one side and basically just slams the piston across the unit to the back inside. And if you wanted to go the other direction, you just put air on the back side and it pushes this piston forward with pressurized air. It has very low upfront cost for the cylinder. We're talking anywhere from 20 to hundreds of dollars is kind of the range. It gives you moderate life. It gives you very high speed, high acceleration, high shock and vibration. So it's able to do high shock and vibration because of the media that's in here is just air. So air is compressible. So it'll absorb that shock and vibration and not cause any damage to the system. And it's good for pressing and load carrying applications. The cons of air cylinders are they're really difficult to do position or velocity control because it's more of a bang bang device versus a finite level of resolution. They do have high install cost, even though the cylinders are low cost, and it's high install cost because you have to have a compressor and you have to have fittings and piping and filters and all this stuff going throughout your plant. There's also very high maintenance cost for mechanically, because if you imagine as these things bang back and forth, it really hits the mechanics hard, hits the fittings, hits the welded on connection points, etc. And it's very low efficiency. It's about 20% efficient. So imagine if you had 1,000 horsepower compressor and you had a whole bunch of cylinders in a plant, you're going to have about 200 horsepower worth of actually work that's done. And in a lab environment or something that's quieter, they're very loud because they're literally like they're a bang bang device, just either on or off. So that's the pneumatic cylinder overview. Going the next level up, a hydraulic cylinder. A hydraulic cylinder is pretty much the same thing as an air cylinder, except you're using hydraulic fluid as a media. It's the same principle. You put fluid into one side of a piston and it pushes the rod back and forth and vice versa. They do have the highest load ratings, just because of the way a hydraulic cylinder works with just filling it with oil. It's not, it has a lot of force per area. They have pretty high life. They're moderate speed, moderate acceleration. They also have very high shock loading, just because, again, it's a media and there's no metal-to-metal contact inside the actuator to actually deform if you do have the high shock load. They have very high pressing applications. So they're really good for push-pull solutions. So the cons are they're very difficult to do position control because it's a fluid and you have to meter it, and it's really hard to precisely control the position or the velocity. They do take up a lot of space. You have to have a big HPU that typically has anywhere from 10 to hundreds of gallons of fluid, depending upon how much volume you have in the system. You have to have hoses and manifolds and actuators. So it's kind of it's a pretty high expense to get into this application. It's also dangerous. The liquid is flammable, so there are fires, and the pressures are dangerous. You're talking 3,000 to 5,000 psi. So if you get a pinhole in a hose, that can actually take someone's finger off, or it can really injure someone. Maintenance cost is high because you have to change the fluid every year. It's just like the fluid in your car engine or your transmission, it does have to be changed. They have high energy consumption because the HPU is always running. It's always on, even if the actuators aren't running, because you have to maintain that pressure. They're noisy, they're hot, they have low efficiency, and they have a high environmental cost with oil usage and oil leaks. Hydraulic cylinders are heavily prevalent in the mobile equipment industries for backhoes and bulldozers and tractors and that stuff, just because they have such a high force per dollar. And they also have a high force per frame size or per density of the application. So that's kind of the overview of a hydraulic cylinder. We'll go to the next level, which is a screw-driven actuator. So a screw-driven actuator comes in three types. So you have a lead screw version, and a lead screw is basically like a nut and a bolt, like you would get at Home Depot. It's just a threaded device, and these devices can be plastic, they can be bronze, they have different materials you can use. The next level up is a ball screw, and a ball screw actually has balls that are in contact on a ground or rolled screw to give you linear force as such. And then the next step up, kind of the highest performance version of this, is what's called a roller screw. And you have a ground screw with this nut that has all these rollers or planet carriers inside. And all of these planet carriers are engaged on the screw, and you get significantly more force and significantly more life. And we're talking low cost, average cost, high cost, and life goes accordingly to that. And these can come in two different flavors. They can come in either a carriage style, as such here, where the carriage would move back and forth, or they would come with a rod style where you have a flange and the rod would go in and out. So there's a lot of these out in the industry. They have low to high load ratings and low to high cost. They're very stiff because they're mechanically coupled. There's metal to metal contact, so it's a stiff application for machine tool or pressing or those type of applications. And life is dependent based on what we're talking about, based on the technology. They can go high speed and they can do high acceleration in the roller screw and ball screw family. They're great for pressing. They do high position and speed control. They're relatively compact for their force they can create. Moderate maintenance, you do have to lube them, you do have to oil them. And the ball screw and roller screws are very high efficiency, 95% or above. Lead screws are typically very low in the 30 to 50% efficient range. The cons of screw technology, they do have a high upfront cost. You have to worry about alignment, you have to worry about the environment, and they're not great for shock and vibe applications. They're also very limited in the screw length, and that's because of two factors. It comes down to what's called screw whip. And screw whip, if you can imagine, you're spinning a really long shaft and it turns into somewhat like a jump rope, and it'll start spinning around and then you'll destroy the equipment. And then also the column strength. So as the nut goes to one side of a screw, you have a column strength that's has to be able to maintain that force along that axis. So that's the screw-driven actuator component. Now we get into belt-driven actuators. I'm the representative for Macron, so we have a couple of Macron pictures up here, but basically you have a belt and some pulleys, and you end up putting a motor driving this shaft, and you can move that carriage back and forth. These can actually be compounded to XY, XZ, XYZ, so you can actually make these into fit the application down to where it needs to go and move in 3 dimensions. So the pros of a belt drive, they can go long stroke. We've done hundreds of feet of stroke with a belt drive. They do low to average load ratings. They have very high life because they're using a timing belt. If you can imagine the timing belt or the serpentine belt in your car, those things are good for 100,000 miles before they have to be changed. It's the same technology that's used in these belts. Very high speed, up to 7 meters a second, high acceleration, moderate shock load because it is a belt. It does have some lack of stiffness that's in there. You can do very high position and speed control, very low environmental impact, low maintenance because there's really nothing to maintain except making sure the bearings are lubricated properly. Very high efficiency, and you can use them for multi-axis applications in a compounded fashion in pretty much any envelope you want, from say the size of a desktop printer to the size of a big rig. That's the envelope space. They do have a high upfront cost as a COM. They're not very stiff, and they're not good with pressing applications because you have a belt-driven component. So that's belt-driven actuators. The next technology, we're kind of going up the food chain here, is linear motors. Linear motors, I'm the representative for Linmot for the Reynolds territory. So if you can imagine, this is a rotary servo motor where it's laid out in a linear fashion. This rod has magnets, north, south, north, south, north, south. And then this device here is able to commutate to move this shaft back and forth at very high speeds, up to 7 meters a second. And that's how they work. You can get these where they have the bearing structures in place, without the bearing structures in place, but these things can literally run billions of cycles. Since it's basically a shaft, there's no gearing, there's no belts, there's no gearbox, so there's nothing to maintain in these, and they literally are just running on bushings and without any metal to metal contact that has to be maintained. So the pros are they do have average load ratings, up to 200 or 300 or 400 pounds. They have the highest life of any technology, super high speed, super high acceleration, low shock load, meaning that they can't maintain their position very well if you give it a big shock, because there's no mechanical advantage to keep metal to metal contact to kind of hold that thing stiff. They do great with position and speed control. They're compact. They're pretty easy to install. The lowest environmental impact, because there's nothing there that has to be maintained. There's no oil or there's nothing like that inside. Super efficient. They also are environmentally one of the best technologies for the most harsh environment. So say IP69K, wash down, steam, caustics. They have IPs up to the stainless steel versions up to IP69K that can accept all that. The cons is they're very expensive. They're the most expensive technology for pound of force. They're not stiff, and you can't really do pressing applications. These are also really great for doing air to electric conversion. So if we go back to the air slide before, where you're talking something that's 20% efficient, these are 95% efficient. So as you look at the cost of ownership and the cost of electricity, there's a lot of these sold in the air to electric replacement. So the last is rack and pinion. These are typically, you can look at the unit and tell exactly what it does. You basically have a pinion gear on a piece of rack, and it moves. And that's how you move the solution, move the application. It's very well recognized in the CNC world. This is the prime mover of many CNC machines on the market. They have low to high load ratings, unlimited travel links that you can just stack more rack pieces, just make it as long as you want. Average speed, average acceleration. They have great positioning control and speed control because you have a direct contact to the load. They have average install cost, very low environmental impact, average maintenance, high efficiency. They are expensive up front. You also have to be careful about how you align them and make sure your rack is aligned with your bearing structure, and so you don't have side loads or axial loads that impact the pinion. And there's no pressing applications, so they're not real good at that application, at that style of solution. So these are all kind of the generalities of the technologies. We could go to many levels deeper in each one, but just for the field, as you're out there, out and about, and you see projects, what is needed to select the proper solution? And Philip aligned on it earlier is you need to know the orientation, horizontal, vertical. We need to know what kind of speed you're looking at, the strokes, the motion profile, duty cycle. What kind of resolution do you want? Forces, loads. There's the environment's a big factor for this, because the environment that kind of determines which solution is available. And then a budget. So it's all the standard questions you would ask. I would throw in the extra thing you would need is what's the moment loading on the device, especially a linear actuator. The moment loading is important to make sure your bearing structure can handle it. So I guess that kind of closes up my part of it. I'll leave you with this. As a sales organization, one thing to think about is the mechanics on a project are designed first. So if you're there in the beginning, you're there to the entire life cycle of the application, and inquire about the mechanics while pursuing a motion system. The mechanical components are typically 4 to 10 times the value of the motion hardware. And it's typically an easier solution to get. There's nothing to program. There's no buses to worry about. There's no, voltages. It's just a lot easier to apply, and it's typically fairly expensive. So that's kind of my part of it. Thank you very much. I'm going to turn it over to Eric Bombier, and he's going to take you through the next section.
Thank you, Rob. Hey, once again, good morning, everyone. I wanted to say also thank you for your time and participation today. Our kind of third and last topic this morning is around machinery safety practices, update, some technologies, etc. I'm Eric Bombear with Rockwell Automation based in Dallas. I've been with Rockwell for a pretty long time, 32 years. And I've seen so many changes in this subject of machinery safety. Things that we used to say you could never do, like use a PLC or network software for safety, we do routinely now. So it's a really dynamic area, something I've specialized in for several years. We'll start with just a little bit of fun, maybe kind of trivia point. Is anyone familiar with what I'm getting at here? The first law of robotics. Maybe you've seen or heard this. This is actually kind of imaginary. It's fiction. But to say that over, I think like 75 years ago, a very creative author made a series and included this of the laws of robotics. So we'll kind of expand on that, recognizing that was based on fiction, but now going through today, maybe sort of a prediction. So some of the key themes we'd like to touch on now are what are the right way to approach automation and machine safety design? And I'll say, how can we do that together rather than thinking of them as separate disciplines? And then we're going to hit on some relevant standards overview and particularly touch on some updates to these key safety standards. And then just a brief view of the supporting technologies, what's new and emerging in this area. So each one of these subjects could probably be an hour or so, and I'd be happy to spend more time with anybody afterwards. I won't cover 3 hours in 15 minutes. Don't worry about that. But just to know there's a lot more under the hood here. So thinking about in context, what's going on in different sort of manufacturing scenarios and different types of machine applications. Although we have a robot in a couple of these, you might say CNC, manual drill press, perhaps. The key point here we're illustrating is that it's really common, and it's getting more common for people and machinery to interact. And we love our first responders as shown here, but we don't really want them coming to our workplaces unless needed. We want to protect people. This headline says people are the priority. I probably should change that. I'd say people are a priority, certainly maybe a very, very high priority. At the same time, a priority is productivity. So we have to have automation and safety systems that enable both. And we want to avoid different kinds of injuries, such as minor cuts and scrapes and bruises. Those might be in some people's minds in safety assessments as acceptable. But we would like to minimize those. And then typically major would be broken bones, amputations, fatalities. Those are not acceptable in our workplaces by any organization. So that's what we have to work to do it. And the way it's kind of been done for many, many years, and still to some extent sometimes today, is to let's put guards and fences and cages. Let's separate physically, mechanically, separate the machinery and the people, and then add something in like an e-stop button that, hey, if something doesn't look right or something seems perhaps quote unsafe, hit the red button. And then to use lockout, tagout for machine access, where we have to maybe go in and make adjustments or thread things up or clear a jam. That's been kind of the mindset. We certainly have new approaches and new technologies. So now, increasingly, we want to see ways to enable people to work with or near side by side. Here, this worker is actually touching this type of robot, collaborative robot. So we want to select the right safety devices and functionality or safety functions to enable workers to be highly productive when working close to or in conjunction with machinery. And then certainly recognizing OSHA's lockout tagout requirements and evolving, in fact, new versions of a standard that might impact that, to maybe we can enable machinery to be worked on in some tasks without having to use hard old school lockout tagout. So that's one view of it. You know, when people have to work close to or with machines. What about kind of the other view? What about when machines get close to people? So autonomous mobile robots, things that move and transport materials or supplies within a facility. We have to think about what type of safety devices and safety functionality to provide there. So the right approach, the way the standards say we should approach this, is to begin with a risk assessment. This isn't particularly hard. It's not really that complex. It's just a methodical way to think about, discuss, get different views, and then write down brief statements of what the hazards, what the job tasks are that might be exposed to those hazards, rate them, grade them, score them, and then to decide what can we do to reduce the risk associated with that task to an acceptable level. That's it. Not hard, not difficult. We can help with it. We have services to do that. We can show you how in minutes, or we can engage for hours or days to work together on it. Functional requirements documentation is a kind of a pre-engineering statement that says how those functions should be designed. Then we get into the real engineering, selecting devices, making schematics, programming, etc. And then to verify that design using some math tools I'll touch on later, is to verify, did our design satisfy the risk assessment and requirements documentation. So verification is an extra step, again, not particularly hard or complicated, and it's something we can help with. And then ultimately to install it and validate that system. So validation is kind of like a checkout, but a checkout on a little bit of maybe amped up steroids. So instead of just saying, I press the e-stop button and I see things stop, we might do things like, oh, what if I have a short circuit in this safety system? What if my light curtain output gets disconnected? Or what if my Ethernet connection to my safety control becomes disconnected? Then we're going to actually validate by injecting faults. And again, not particularly complicated, something we can help with, and we have some tools to really streamline that. And then ongoing operation, maintaining, improving. This is the lifeblood of the machine and system. If there are changes needed to production, to throughput speeds, etc., then we would walk back through a risk assessment cycle. Where does that come from? So what are the sources of that approach and those engineering requirements? Well, I like to kind of emphasize the US, or the American National Standards, so ANSI. And ANSI B110 is the foundation of machine safety in industry. It provides techniques and methods to guide risk assessment, preliminary design and mitigation decisions. And it really is foundational to, I guess we could say, all industrial machinery used in the US. Now, it is an ANSI standard. I will point out it is very tightly aligned with, or we call it harmonized with, an ISO standard. So in many of these cases, the American National Standards and the ISO or IEC, European, regional, etc., are very tightly aligned today. So I'll illustrate that a little more. ANSI B1119 is a great engineering reference. All controls engineers, design engineers that are working with safety applications would benefit from knowledge of this standard as well. And then I'd like to just highlight ANSI B1126. This is where the real controls engineering comes into. How do we design, assess, and, as I mentioned earlier, verify and even validate our safety designs are valid or accurate. I'll just highlight here, if you notice, these are recent updates. So 2023, 2024, these standards don't just stay written in stone. They do get reviewed, updated, etc. And so just to be aware, there are recent updates on these fundamental standards that we use. And then hot off the press, I think actually last week, is this newly released ANSI A3 robot safety standard. So this is the US adoption of ISO standards with some expansion on putting it in context of ANSI. Some of you might think of ANSI A3, you might be thinking about ANSI RIA, Robotic Industry Association. That association kind of combined and merged and is now referred to as A3, by the way. So I mentioned ISO 10218, and this statement was just put out, I think literally last week, that the American National Standard and A3 are publishing this R15.06, and it's adapted from ISO 10218, which was also updated this calendar year. So just for reference, those are the current, the way we do things in machinery safety, especially robotics. And it provides a map like this. And again, so if you're trying to make sense of which standard do I look to for what, there's no one standard that says everything. They are dependent perhaps upon each other and build on each other in some ways. So this is a handy map for engineers that need to know which standard am I using for which functionality. So what's new? What's new is the standard is adopting some new technologies, especially what we refer to as collaborative applications. The group doesn't like the term cobot. They like to use collaborative workspace, collaborative applications, things like that. But we're talking about people and machinery working closely together. There are new safety functions and testing methods, and then some considerations around end effectors and loading and unloading. So it's been enhanced, it's been expanded, and it's a living document, will be updated and reviewed again for years going forward. So what about security? You know, kind of mentioned that we're now using techniques like Ethernet and networks and software and electronics in our safety systems. And so we now have a stated requirement: cybersecurity threat assessment shall be conducted. So when standards use the word shall, they mean, yeah, we better do it. It's not optional. So considering cybersecurity in context of our machinery safety applications is not brand new, but it's not been focused on in maybe a rigorous discipline as much as we need to do it now going forward. And that kind of ties us into the wrap up of the supporting technologies and what's new. So we're seeing much more use of Ethernet for connecting our safety devices, our safety controllers. Again, something we would never have imagined doing years ago, and getting all the benefits of industrial Ethernet SIP safety to reduce wiring and improve systems. Another kind of development is safety is so foundational now that we're including safety functionality for free, so to speak, in our Logix processors. So we no longer charge more for the safety rated version of our Logix L8 or compact Logix 5380 processors. In fact, going forward with the launch of the L9, which is only hopefully weeks away, safety is no longer an option. Every Logix L9 processor will have safety functionality included. And then we have also developing some new programming, some standardized ways of developing safety application, and some pre-engineered examples. I'll show an overview here of where you can get more information. A little asterisk I put there, safety is free, just to be specific. That is our SIL 2 performance level D. What some might think of as category 3 performance level of safety is the no charge. So here's the big picture of new and developing technologies. Philip mentioned earlier the servos we have, the kinetics on machine. We have VFDs in our Armor PowerFlex. We have things like safety rated encoders, interlock guard door handles with locking devices, area scanners, light curtains. The list goes on, and these are all devices that need no hardwired safety connection whatsoever. It can all be done over Ethernet IP using our SIP safety protocol embedded in. And then over here on the right is another safety linking technology we call GuardLink, where we can put simple devices like e-stops, push buttons, guard door switches into this quote unquote network, which then bridges into SIP safety Ethernet IP in this example. So we can conceivably have a system with very little to possibly no hardwired safety and still meet or exceed all the required standards. So a couple of tools and references to know about and to get people to look at. These are over 200 safety function applications that people in Rockwell have already developed. There's schematics, there's bill of materials, there's even programming segments for your Logix ladder, safety ladder, systemic calculations, and a verification and validation checklist. These are unusual to me PDF documents, is that when they're downloaded, there's a paperclip icon on one of the side panes. And when we click on that icon, we'll see this list of exposed attached files. And I've shown this to customers that have used them, but didn't even know these attachments were here. And then when they realized that, they thought, oh, this will save me days of work. So yeah, be aware of those and reach out if there's any more information wanted. And then I mentioned this safety math, these calculations. There's a tool called Systema, which is an acronym, and we provide a library file for our safety related products so that these calculations can be done in perhaps minutes or less versus maybe an hour or more to do it a manual or having to look for the data some other places. So again, a tool to be aware of and something we can help